turn off camera. Off. There. Okay, here we go, guys. Projectile motion. Step 1 in projectile motion problems. All right. And when I say projectile motion, these are typically things that are at an angle flying. And they have to do this stuff kind of all sorts of places. Everything from understanding rocket flights to missile trajectory, airplanes, all sorts of things. Understanding the best trajectory of throwing a football in a football game, all sorts of things like that. So the first thing is, like we normally do, is we try to figure out what do we know. All right, so we're gonna look for the variables that we know, or known variables. We're gonna identify those, like we've done in the past. Step 2 is we're gonna determine. So from the R, so you're gonna be given the R value. So remember, that's like your resultant value. You're gonna get the hypotenuse. You're going to need to solve Vx and Vy. From there, we can solve for various things, understanding some key concepts. Understanding that Vx is constant. Acceleration in the y direction is constant. And at apogee comes back in here. We know the velocity in the y direction here now is equal to 0. Not the Vx. The Vx is still the same if the velocity in the y direction is 0. All right, so this is like some key points. From there, we can start solving for various things. Okay. So let's look at the last two problems on that first packet. That was like 1 through 6. I recommended we were eventually going to go through. And you guys already did 1 through 4. We just did that like space agency one recently. Okay. So we're going to look at these ones here. And spend some time going through how to solve one of these using this setup that we have here. Okay. Let me make this a little larger so we can see that. Again, maybe you guys have this. If you want, you can look there, or you can just follow along here, write this problem in your notebook. Okay. Go. So we're going to write down what do we know. We know a football player is going to kick a ball with an initial velocity of 25 meters per second at an angle of 45 degrees with the horizon or horizontal. That pretty much just means if I was to draw Mr. Football Player, about to kick the ball. Maybe he's going to punt it, or maybe I drew this wrong. Maybe I should draw it like he's about to kick the ball and it's on a tee or something. He's got his other hand up there for balance. We got to put a helmet on him. He's going to just have a single bar because that's all I can do. All right. There we go. Got a helmet on. He's ready to kick that ball. All right. Now we know that he's going to kick the ball at an angle like so. Just like thinking, okay, he's going to kick a ball. You know, the ball's going to go at an angled flight. That's really what this is saying. We know that this angle here is 45 degrees. And we know he kicks with a speed of 25 meters per second. So that's our scenario. And I'll make this a little larger. Okay. So what we're going to do here is we're going to solve for Vy and Vx. Now, this is something you guys have done before in our previous units. To get Vx, we know this is an adjacent side, then I've got a hypotenuse, so that must mean I'm using cosine. So we've solved for Vx like this before. We took the hypotenuse times the cosine of the angle, okay? Glare, not my friend. Okay, there we go. And then we were able to solve for it. And then we could do the same thing for our Vy. We take the hypotenuse times by sine this time, because this is the opposite of the angle. Okay, so I'm going to start plugging this in. I'm going to have 25 times cosine of 45 equals 25 times sine of 45. And this will get me my Vx and my Vy. So my Vx is equal to 17. I'll just make it 18 just for 2 sig figs for now. And this one will also be 18 because anytime you have 45 degrees, your x and y are the same length. Right? From math class. Hopefully you guys remember that. It's 18 and 18. Now, we're going to again remember one key thing. This Vx is constant. Is my Vy constant? So what really should I define this Vy as? Initial or final velocity? It would be the initial. So that's the initial velocity in the y direction. Initially, what is the amount that the kicker has inputted into the ball to give it a velocity in the y direction? Okay, so this is the initial velocity in the y direction of 18 meters per second. Now, in the PhET simulation, they asked you to kind of do something similar. Here, they said, draw this scenario. So that's what we did. Then use sine and cosine function to solve for Vx and Vy. That's what we just did. Okay, we took and solved for the Vx and Vy of our angled flight. Now, the next step is to start solving for the other parts of the problem. Okay, so I'm going to zoom out. And we're going to solve for a couple things here, which will still use a lot of the same variables. Now, one thing when doing projectile motion, certain things will become constant. We're going to be using the same style of equation to always solve for one particular thing again. Okay? So determine the time of flight. Determine time of flight is going to be taking into consideration, I've got the ball going up and then coming all the way back down. We know that in part of that flight, the ball is going to reach our apogee point. And we know at apogee, we're going to define this now as Vy final, or Vy apogee. But for now, we're going to define it as final, at least in the first set of our problem. It's 0. Okay? So again, we're defining our Vy at apogee as 0. So what we actually have to do when we're solving for time, we actually solve for half the time. We solve for the amount of time it gets to apogee, and then we solve for the rest of the time. Okay? And we've done something like this before with the vertical problem. Say you just shoot the ball straight up in the air, and then it comes straight back down. We did something similar to this with the vertical problem, like for example, right up here with this space thing. How much time did it take to do that? Now, we're going to actually use, the only difference up to this point is doing this here. That's the only difference. So you had to take vectors and put it into projectile motion. Now from here actually becomes something we've done before. Okay? We want to solve for the time at apogee. So I'm just going to say TA, or T half is sometimes how I define it, but we're going to say it's like time to apogee, or TA. We know at that point, our final velocity in the y direction, which is our apogee point, is 0. We know the initial velocity in the y direction is 18. And we know we always have acceleration, which is negative 9.8 meters per second squared. Okay, we have these 4 variables. Can everybody see that relatively well, or is it challenging? You're all good? All right, cool.
Oh, and for gravity and everything, if it's going to be negative 9.8, why do you just put it on?
What?
Because sometimes you want to use 9.8 or 9.81. You always have it on there. Which one will you use?
It doesn't matter. If you choose to use 9.81, you're going to get something very similar in the answer, and I'll be able to tell. So feel free to use 9.8 or 9.81, whichever one you choose. Okay? All right. So if I have these 4 variables, I look at my equations, and I can figure out my answer. Now, pay attention here. Time is still related only to the y. We always usually figure out time based off the y information. Okay, time is again really going to be determined on the y information. All right, so that's why everything here is in the y. Time isn't going to be related to how fast the ball is going in the x direction. All right, so the equation I'm going to use here is this one. Now, in the past, we have had, we've used like this one to like get time when it's falling. But we're not having something fall here. We're having it go up to apogee. So we're going to use this one, not this one. So oftentimes we use like this one with our cliff problems to solve for time. We're going to be using this one here because that one gives us time, has final velocity, initial velocity, and acceleration. So that's the only one that logically makes sense here. Okay? I gotta erase that just so I have more space to work here. All right, so I'm gonna plug in my values. 0, 18, negative 9.8, and t. And a glare. Doing some algebra, minus 18 to both sides. Minus 18 equals negative 9.8 t. Divide both sides by negative 9.8. So my time to apogee, or my t half, is what? Well, I can do it, you're right. But this is different between in person and not in person. I can now kind of encourage you to solve the answer instead of me just doing it for you all the time.
That's just calculators.
Well then, come on, mister. Get your calculator out. Solve it. Let me guess, you don't have your calculator with you.
No, I do. I just don't want to use it.
2 sig figs. I think I heard someone say it. 1.8. So this is time to apogee. So this was our time to get to here. That's only half the time. So what do I have to do to this to get my total time? So 1.8 times by 2 gets me 3.6 seconds. So that's my time. Now again, I'm going to tell you very clearly, time is always going to be defined based off the y-axis. Time will usually be solved using this equation here. Okay, and usually when you're solving for time, you're solving for half the time. Okay? So I'm trying to show you there is some consistency in these problems. Sometimes it looks like there's never consistency, but there is a lot of consistency in these problems. So they don't have to be overwhelming in the amount of information that's there, but they sometimes look that way. All right, so I've got my time of 3.6 seconds. Horizontal displacement is super easy, so we'll just do that one next. This one, like, you guys should like just rock out of the park with this one. So horizontal displacement is dx. Displacement and distance are the same term. In this, like, solving wise, it's the same term. It's not the same term in actually physics, but in this case, it's having you solve the same way. When it says the displacement, it's just saying it's going that way, or whichever way we define the person is kicking the ball originally. Okay? Or for you guys, it's like this way. Okay? So I'm pointing according to mine, so sorry. So I'm solving for dx when I say horizontal displacement. I know my vx is 18 meters per second. And last but not least, I know my time is 3.6 seconds. All right? Now, so I've got all the information I need. I do not have an acceleration in the x direction. Okay, I only have an acceleration in the y direction. We've defined this before. We said vx is constant. So I'm back to using this same equation we've used in the past. So I have 18 times 3.6. Which turns into a dx of 65 meters per second. Or not meters per second, sorry, just meters. You probably got on your calculator 64.8, remember? You need to round that 4 up if we're using 2 sig figs. So that's why it's 65. All right. Any questions this far? No? All right. Yes?
3.6, is that the total height of apogee?
That was our total time, which was our 3.6. So the total amount of time it took to go apogee and then back down. Apogee would have been 1.8. I doubled that to get 3.6, so now I've got the time it takes to go all the way back down to the ground. Okay? So the total time it's in the air. All right. So we've got that. The last one, okay, the last part is I need to solve for, it says the peak height. So I'm solving for dy. And this is really the distance to apogee. All right? So that's what I'm solving for. I know that my velocity at apogee is what I'm going to define as final velocity, is 0. I still know my initial velocity in the y direction is 18 meters per second. And I still know that acceleration is going on because I'm on planet Earth. So I've got these 4 variables occurring. Now I know that there's some things where you're going to have to, again, think through the problems. There are some assumptions that occur, like, okay, dy, I had to make the assumption that I'm going to apogee, and at apogee, the velocity in the y direction is 0. Also, I had to remember to make the assumption that I've got acceleration of gravity occurring, which is negative 9.8. It's not stated anywhere in the problem. We have to think about the problem, think about this scenario, and go from there. That's what we need to work through. All right, so I've got that in our problem here. Now, next, we're going to be using this equation because it's the only one that logically makes sense to solve for the distance. And again, this should look familiar to your vertical problems because you use the same equation to figure out the height to apogee in the past. So you are aware. Now, why didn't I use time to apogee? Why didn't I use that 1.8 seconds? Hypothetically, I could have. Okay? However, that 1.8 seconds, I'd have 2 sets of rounded information there, and I'd prefer not to use that. I'd prefer to use 1 variable that was only rounded instead of 2 to get a more accurate answer. Okay? But hypothetically, we could solve this part in 2 ways. Okay? So I'll show you the second way here in a second. This is the first. So 0 squared equals 18 squared plus 2 times negative 9.8 times d. 18 squared is 324 plus negative 19.6 d equals 0. Subtract 324 from both sides. Due to algebra, adding those together, so they got to be subtracted. And I put a line there. Negative 324 equals negative 19.6 d. Now those 2 are times, so I got to divide. So my d is 17 meters. And it's not negative because it's going up. Okay? It's not negative because it's going up. All right. So this is the kind of like the main thing that we'll be doing is we're mainly going to be solving for the dx, the time to apogee, the maximum height at apogee, so the dy. Those are the main variables that we're going to be solving for in these problems. Now, the difference though is with the hoop example. With the hoop example, you would have to use time to do things. So like, for example, if we've got a trajectorized flight and I want to put a hoop at certain spots, here, this is all going to be based off of the time at each of these points. Okay, the time at each of those points will determine where I put it in the y direction and where I put in the x direction. Okay, so I'm going to show you how to solve this same one here for dy knowing my time. So I'll show you this one knowing my time. So you get an idea how would you solve for the, if you have the time given instead. So here I've got my time was 1.8. This is the time to apogee. My don't have to worry about my VF. My initial velocity in the y direction was 18 meters per second. My AY was negative 9.8 meters per second squared, and I'm solving for dy. So here, I'm going to come back to this equation. That we have used in the past. So this time, though, we always cancel this out because it was always 0. Can't do that anymore. So it's 18 times 1.8 plus 1/2 negative 9.8 times it by 1.8 squared. So now 18 times 1.8 is 32.4 plus negative 4.9, so 1/2 times 9.8. 1.8 squared is 3.24. So times 3.24 by 4.9, negative 15.876 minus my 32.4. So finally my dy, well, I take 32.4 minus 15.876 is 16.5, which we round up to 17 meters per second. And we have solved for dy in 2 different ways and gotten the answer correctly. So again, you can do it in 2 different ways. So it doesn't have to be done the way I showed you, but this is sometimes going to get you a different answer because you're going to have to round more. Okay. Now, some of this looks like really fictitious and like, oh, this wouldn't work. The way you're doing your math is faulty or things of that nature. So we're going to actually look at a real life cliff style problem that the Mythbusters tested for the remaining time in class. So we're just going to start here. And here are my expectations for tonight. Okay. Or if you want to do that during the Mythbusters thing, you can choose to do that too. Okay. So my expectations tonight is that you try number 6. You will never, unless you are somehow smarter than me, and if you are, thank you for solving 7 and 8. But they're almost impossible from my own current brain power to solve 7 and 8, so don't try. All right?
Yeah, if we solve it, do you extra credit?
Well, if you solved it, I wouldn't be able to tell you if you got it right or wrong, so we're not going to try it, okay? All right, so you guys are going to try number 6. And if you haven't finished the calculation problems on the FET lab, you're going to finish that as well.
Alright.
Okay? If you didn't solve the FET problems correctly, you're welcome to resubmit that part if you would like. Okay? Now, so back to the thing at hand. So that's the plan for tonight. I want you to work on just those two things. Okay, is this thing gonna pause?